Welcome to our next trees video where I'm going to give you a basic quick introduction to the idea of game trees. Before this we've gone through the basics of trees to give you an idea of what does every tree data structure generally have and some of the tools. We then covered binary search trees, which allowed us for quick storage and retrieval of information compared to just general lists. And now I just want to introduce another kind of application that you could have a tree, since there's a wide range out there. But now we're going to step a tiny bit into the AI realm, working with game trees. So a game tree is a form of decision tree. So here it means that the nodes represent possible positions as states in a game, and the edges represent the moves. So again, you think the nodes are, this is the actual game, the possible move, and edge means transition from one board state, so where one player's made a move to where another player has actually made a move. It can be thought of as a multi-person decision tree, so instead of just going through to make one decision, it represents the choices for both players, but coming from the standpoint of well, if I'm an AI and I've got to make a decision of what move to make currently in the game, what could I look to in the future for different possible moves? So an example here, if we look at the base game of tic-tac-toe, where you have two players and you're trying to line things up to get X's and O's, you could start with, hey, if it's the very first move in the game and the AI is supposed to make a choice, they're presented this empty board. And then next they can look to, okay, well you have these three edges and you have the three possible, right here, example of moves you could do. And really there's 9, so imagine this tree being even larger, but this is example here. But these are just other possible moves that the AI could make. Then another level down is then the moves the other player could make based upon this previous one that we saw. And so forth till we stop at a certain level. And the idea is that it's really just trying to look to the future, usually to a certain level, and then evaluate, well, what was the end result of that entire path of all these branches, and then kind of bring that value back up to the top to make a decision of, okay, well, what do I do up here at the actual top? Which choice do I finally actually make? So it is used as a way to evaluate the possible choices and come to a final decision of that move, what move should be made during the current step in a game. So a new game tree is constructed and searched each time a decision has to be made about the action that should be done based upon the current state in the game. So really it's every time the AI needs to make a choice in the game, it's going to rebuild a whole new brand new search tree based upon the current state in the game. So every time it's its turn, it's going to do this work. So a complete game tree is the game tree starts at the beginning point of a game. It then contains all possible moves alternating for each player until all possible terminal leaves nodes have been found. And so these are the win-lose cases. Now this is the ultimate, really realize we're not going to always get this. This means a complete game tree, literally is doing it all the way to the end. So the current state and going all the way to the end of every possible combination that you could have and getting to all the win states and all the lose states for the endpoints of the game and evaluating and coming back. And that's the complete game tree. But there's issues with this. Depending upon the number of choices, this could be massive and take way too long to complete. And so we'll get to later on where I mention the idea of partial game trees is what we're really doing. But right now we can think of an overall game tree. So the number of leaf nodes in a complete game tree is the number of possible different ways the games can be played, i.e. the complete end results. So if we go for an example again of tic-tac-toe, the first level would be the empty board. The second level contains all possible moves for player 1. Third level contains all possible moves for player 2 based upon the moves from player 1 all the way down. And all levels are built in a similar fashionable way until we get to terminal win-lose conditions. Now for tic-tac-toe itself, the complete game tree has roughly 255,168 leaf nodes. So that's possible. And that doesn't even say how many nodes you have before then. That's the end results, where a leaf node represents a terminal endpoint for a game of someone winning or losing. So the game tree tic-tac-toe is easily searchable because that's still a small number, and we can build a full tree and check all possible paths to leaf nodes and not have to take an extremely long time. So that's for tic-tac-toe. But if you took something more complex like chess or Connect N or other games where the choice can be larger, this can become really difficult. So even visually, here's even just a small example of trying to do that complete game tree of going through all the way down to the end of possible win or lose states. And like really the fact is that this is not even the full tree, is that we'll have like the 255,000 just leaf nodes, let alone like all the ones you had before it. Now, visually, before I go on with showing more of this, when we get into partial game trees, an actual algorithm that's used that constructs and evaluates the game tree in one step, I want to just show an online simulator. You have one right here. So you can click that link if you're at home if you want now, if you've got the slides, or go to it. MinMax Visualizer there. I'm just going to go switch to the one I already have open, and this is where that you can start playing the game against an AI, and the way that it's only going to go down to certain depths we'll talk about in a second. So this is tic-tac-toe, and it's going to go through all these choices and do the evaluation. So every time I do a move, it'll rebuild the tree and automatically have the move between the players. So starting with is that player X is the human us, and player O is the AI, which is using a MinMax algorithm that we are going to talk about just shortly. So even if I just start, I'll just start playing the game. I've got my X here, and then the AI automatically choose to do over here. And you can kind of see the evaluation tree that has been built up, and just start to see here, going to level of 2, of all it's doing is from this game to the next choices. So from this player to then all of the other choices coming down from here. So possible choices of what could be done. So if we're starting from this game, and now this is a MinMax tree that's being built to represent possible choices of what we could do from this state. So we have here, going down to what we could do, going down to further evaluations from right here for what the O player could actually do. So our moves, so current state, at the top, all of our moves being the next, and then the further down is all the moves the other player can do. And this is only going down to 2 depths here. And then we can see evaluations of what's good or bad from right here. Lower numbers are bad, higher numbers are good. So any of the states that we can see coming down from here where they've got the zeros can be good, but where 10 could be the highest is leading towards where we could do better choices of what's coming from here. So I can even start looking, okay, if I put X down here, it seems to be saying that this, this, and this, and this are all good so far. And then we got the minus 10s to 10s to minus 10s, and I'm like, I probably don't want to do this because there's one good 10, but the other choices are all bad. Whereas this one over here, there's a bunch of 10s, little 10 zeros, and same thing here, and same thing here, where there's nothing good past like the zeros, and the highest here is 10, where there's 2 10s. Here are these 2 10s, so I think I should probably pick this choice here of the X being here as a better choice. And so the AI is going to be doing the same thing, building the tree to make its decisions from here. So I'm going to pick this based on what we just saw there. And now it recalculates. Now automatically, I don't even need to look through this tree that this would be horrible. If I don't cover up this spot, they're going to win. Which automatically means that they'll detect that they should do the 0. You can see that. We have no choice now. You can see all the choices become limited because we only have 3 choices coming out of here. All of these are bad. Nothing is much better. But from this one right here, of the choice where, let's see, where you put X down the bottom corner, or the bottom, seems to be that we have a better chance right there. Boom. But they won no matter what from right there. So boom. Now we could start this again by going and looking further into the future, which just starts getting to be a crazy tree to evaluate this. So we'll reset everything. We've got 4. I'm going to start in the 0 in this time. And then that O player made here, but look at all the possible choices that you could have just going down a depth of 4. Like this starts being just a little bit crazy to even see everything that's happening here. But we've got to start making decisions of, okay, well, what would be the best choice to actually make coming out of this? It's kind of hard to see from here. I'm going to go down to this 3. Update the tree, and even there it's still hard, but this is where it's trying to evaluate and going a little bit further. So all our moves, all their moves, and then all our moves coming here again, so maybe it'll come back with better results. And I'm just going to scan quickly from the top here, seeing zeros, okay, seeing anything that would hopefully start going to a 10 to start with. And there's nothing that's coming out that is good. So I'm just going to arbitrarily pick down here for this corner. I've got no choice, got to block them. Got from right here. Okay, well this is a smaller tree, so let's see what I can start seeing. So again, these seem to be all be evaluating the same. Right here, minus 10s, minus 10s. These are zeros. Maybe this is looking better, so let's see what move this is. This seems to be up to here. So nothing much better, but there's not more horrible cases of them winning. So go from right here, and now there's literally no choice, and at least we got them to a draw of looking what's happening in the future. So they're using that same algorithm. We're using it to evaluate from the future. This is just a quick one. You guys can go and play with this one, but I'll start talking about the algorithm next. So let's switch back to the slides right here and just go on. So partial game trees. So the other one's a complete game trees for larger games like chess are much too large to search. Instead, a chess playing program searches a partial game tree. So something that is that you don't go down as far. So as you saw from the other example, they only went to a certain depth. So this is basically trying to go down to typically as many levels down in the tree for the current position as can be searched in the time available. Because if it's too large, it can take way too long for the AI to actually make a decision and make the game useless overall to do it. So you'll go down to a certain number of levels and you're trying to optimize. If you can make your algorithm faster, well then you can then go look further into the future, maybe get better results and make your AI better overall, combined also with what's called an evaluation function. So starting algorithm, and there's lots of other game trees that are out there, lots of other algorithm stuff you're working with. We're just going to start with by looking at the MinMax algorithm or MinMax algorithm. So its searching of a game tree is done using the MinMax algorithm or a variant of it. It minimizes the impact of the other player's actions while trying to maximize the impact of our actions as it works its way down the tree. Now, compared to the binary search tree where you built the tree and actually had nodes and then used algorithms that may have been recursive or iterative to go move through the tree, the MinMax algorithm really uses recursion to create the tree and evaluate it at the exact same time. So you never have the full tree. You're basically stepping through the entire tree structure, and as you do the recursive steps, you're passing in the new nodes you'd expect below because you don't need to build the tree and then evaluate it as you work with it. And so you use the power of recursion and multiple recursion and basically doing a post-order traversal where it goes all the way to the bottom first and then coming back up, because this is a traversal algorithm, being that it has to visit every node in the tree at least once and do some work, where here it's evaluating the quality of steps as you move back up in the tree, maximizing our choice while trying to minimize their choice to get an ultimate decision up to the first children node that come off of the root to being, well, what is the action that we should be taking? So assume that the algorithm here assumes that the opponent is rational, i.e. can compute moves just as well as we can. We'll always choose the optimal move with the assumption that we too will play perfectly. It's built into the algorithm. So if it's a little bit chaotic, who knows what could happen to the algorithm. So here is the basic pseudocode of it. You guys don't need to know this perfectly, but this is to show you, and I'm going to link to Wikipedia where you want to look at it more, and you can find tons of examples up here. But this is generally a recursive algorithm. So it uses recursive method as a way to start stepping through the actual tree called MinMax, where it's given a node, the current depth you're on, and who is the maximizing player since you're switching between it. If we're at a depth of 0 or no node, or there is no, or node is a terminal node being your win, then it means here. So it means you just return the evaluation of this current node. So what this is that for the depth, this is how far down you want to go. So you set this being like 1, 2, 3, 4 levels. Generally, you're at least doing this to a depth of 2 because you want to go for not just one depth of like, okay, from the root to our choices, but you want to at least go to the other player's choices. So it's usually a minimum of 2. So it's going to stop recursing and be your base case when we've hit a depth of 0 and you've hit the terminal node, meaning there's a win or loss or draw. And otherwise from that, then you just return back the evaluation of this node. Otherwise from this, and I'm going to go through the slides from here, it goes through saying, okay, if we're on our maximizing sides, it tries to pick the evaluation that has the highest evaluation. And if we're on the other player's side, we're trying to pick the one that has the lowest value from right here. So depending on whose turn it is. So is it our turn or is it their turn? And you can see here the recursive step. You can see right here, which is the MinMax algorithm. You can see the recursive step where it's subdividing it by what depth you're going down from right here. And the step here is for each of the children nodes. So this is the new steps it takes. That is where it's evaluating from the current parent that you're coming in. So the node that we're at, where the children or possible moves you can make off of this, and saying that now, okay, these are the children based upon it being the other player's choice, and then the evaluation after. And the key thing is this evaluation is done after, so this is what makes it a post-order traversal, that it will go all the way to the bottom of the depth or terminal node first, and then evaluate that, and then start bringing it back up there before it comes to this node. So it'll go to all the children first, then come back to the parent, and then the parent above this, and so forth. So the algorithm, so you analyze it, you reach an end depth, or someone has won, lost, or tied, so that's the depth 0, so as far as you want to go down, we return the evaluation. Now, this evaluation function here is going to be really important because this is saying what's the quality of this board, which really determines how well the algorithm works. So in the end is MinMax algorithm goes through optimizing and trying to pick the right choice, but it's really dependent upon the quality of your evaluation that says, well, what's the quality or worth or strength of the current board state? Now, when it's recursing down, you'll see when it's our turn, you're seeing if it's maximizing players true, then you just start setting, okay, the first one, best value being the smallest you possibly get. And you're really just doing a search for what's the largest. So you go through for each children, so the current state, you're then calling and say the evaluation going down, and you're saying, okay, what's the next child, which would be based upon the move we have, what's the move that the other player could do, so that's one of the child, going one depth down, telling the algorithm now it's not the maximizing player. Once you get the evaluation back, you pick the best of, well, what came back versus what you've seen before. So always trying to see what's the highest evaluation that came back and return that going from there. If it's their turn, it's basically the opposite, that you're going, okay, well, what's the smallest value from here? So we go through all the children for the choices that so from their current board, the choice that they made, what are the children for the other player, being the AI, going one depth down here and picking from here what's the minimum value. So when it's their turn, basically we're trying to pick the minimum evaluation, and when it's our turn, we're picking the maximum. And this is going to be for each level. So if it's on a level where it's a choice that we've made, then it's going to pick the maximum. If it's in a level where it's a choice they made, we pick the minimum, and it goes back and forth. So always trying to pick where it's the highest when it's our turn from our choices. Now the starting call of this is you start the min-max giving it the root, which would be the current state of the game. You give it the depth you want to go to, and you start that it should be our turn. So root is current game, depth is the number of levels you want to go down, and true indicates that it is our turn to actually evaluate. The final decision of what action to take is done in the following way. So get all the children for a root node. So this is after it's evaluated everything, so it's gone all the way to the terminal nodes, the end. It's come all the way back and evaluated every single node, and you're done running the min-max after that. And then the idea is then the algorithm takes from the root node that it had down to the first level, being the children, and picks the one that has the highest. So it gets all the children from the root node, finds the child with the highest score after running the min-max algorithm. If their multiple children have the same score, it picks one at random, and it uses the move from this chosen node as the action that you will run. Now, how long does this algorithm take? For a simple game like tic-tac-toe, not too long, even with a complete game tree. For a game like chess or Go or Connect N or checkers, however, the running time is prohibitively expensive because the number of possible choices, and if you can make it smaller or do the choices limit as you play the game on. So therefore, all real computer games will search not to the end of the game, but only to a few moves ahead, being a partial tree. And that's using the min-max. There's probably more complex algorithms or faster computers that can handle larger scales of this. So the program must determine whether a certain board position is good or bad for a certain player. And this is really important for the quality and the strength of this algorithm, where a whole bunch of people could just use the min-max algorithm or slight variations of it, but the real strength of it comes from the quality of your evaluation functions. So this is often called an evaluation function. This function is key to a strong computer game. It does little good to be able to look ahead 20 moves if how you are evaluating it is crappy. So let's run a small example on a board of the tic-tac-toe game using a partial game tree down to a maximum of 3 levels from the current state. So it means from the current state, then it'll go to the AI's choices, the other places choices, and then our choices even further in the future. And the evaluation of a node returns back the longest chain length of tiles for the current player. So it returns back, okay, how long of a chain do we have? We're trying to get to 3 for tic-tac-toe. How do we have? And so higher should be better. And so let's say the game has been played for a while, and this is the current state that the AI is given. So this is what board it has from right here. And currently X's turn. So we're X, the other player is O, and this is the board that we're starting with. So when it's first our turn, we start passing our min-max. We have node, going to level 3, we're going to... And so from here, we want to then generate all possible choices we have. And so with tic-tac-toe, it's what's open. And so we have what you see, the 3 that are the yellow choices where we could have X's placed. So let's say we do the first one here, and this is what's going to be doing for the recursive algorithm, that it's going to be going down to a depth and starting. And the order, if you're going from which choice pieces due to like what order you go through the children when you're doing the recursive function. So we'll say from right here, okay, well, what if this is the board that we place X here, and then now it's going to be going from this level as the other player's choices. So from there, it's then, okay, well, this is what the other player could do. So if this was our choice, what if this was their choice? And then finally going down to where it's not a terminal node. Here we're hitting a depth of 3. So 3, 2, 1, 0. Going here, and then saying the last choice. And so then it's got to go through evaluating this. Now, if we're looking through this, we have to look through all possible combinations we could have. So there's a length of 1. Here's a length of 2, 2, 2, 2. So the evaluation on this one would be 2. That's coming from here. There's no children, so this would be returned up to that one. So that's 2 for the one choice that came up. Now for here, we're coming back up to the board. There was still another choice, there was no other choices, so we came back up to this board and we see, okay, are there any more choices that could be done from here? Well, yep, they did O. Well, what if they did O down here instead? So they had those 2. Then we go down to here, and we get to a case where it's a little bit better for stuff. So again, this is just going through all possible choices. And we came here, they could have either gone here or here. So the first one was where they did here, like this one. The second one here is where they did here. Go down to another level. We can then see we do a terminal because we're level 4. In this case, we have 2s, but we have a case of 3 as an evaluation for longest chain. So 3 would be coming back up here. Now remember, in this case, is that in this level, we're coming down these choices, but here we're trying on a maximizing level for right here for what we come back. So this is minimizing from everything else they had here. So coming back up from right here, we want to pick the maximum between the two of these. So 3 will get moved up. Well, sorry, minimizing. Sorry, so this is the call going down here, so it's wrong. This is the minimizing because this is where it's the O's choice. So this is where maximizing, minimizing, maximizing, because our turn, their turn, our turn. So from right here, we're trying to minimize. So it comes up to here to being the 2, because that was the minimum out of these 2 values. And now we're done that this has no more children, so it'll go over to here, and that was the one choice. So now here it'll do the other choices. So really, we're just going through all combinations. So again, the middle one has 2 choices, so we do the 1. There's a terminal node, so it stops because there is a win from right here. So we stop. We get an evaluation from right here. The longest length is then 3. That's coming off of this board. The next term right here is this is not a terminal node, so it made the one choice from right here is that O went there for their choices. Then we have what we could do. So we also get an evaluation of 3. So here we have 3 and 3. So maximum of that is 3 comes up for this choice. And then finally the last choice possible that we could do here, going through all the choices. So terminal again, 3, go right here, another choice, 2. So 2 comes up here, here's 3. Here we're trying to minimize on this level, so we pick 2. And then finally, right here, we're trying to maximize, so we pick the highest, so we get 3. And 3 comes up to here, so this means this is the choice we will actually make. So from this board, this is the choice that we'll actually make, which is going to be bad because then they're just going to make this move and they're going to win. And so the algorithm went through the steps of evaluating everything, but it was the evaluation function to detect, hey, this is really bad. Like, we shouldn't have allowed this. We shouldn't allow their wins, and it should be higher when we had our wins versus when they had theirs. So there we go, the move that they'll actually make. So let's try just doing the same algorithm but using a different evaluation function, so evaluating the node. So if we have a win for user, we're going to return 99 right here. So if it's a win for us, return 99. It's just some really high number that's beyond any evaluation, because 99 is beyond, like, you're never going to have a length beyond 3 if we're doing the nodes. So here, if there's a win for them, we return minus 99, so it's the lowest value-wise. Otherwise, find the longest chain for the current player, count how many of these chains we have, call it n, count the number of chains for the other player that match the found length for the current player, called m, and return n minus m. And so here we're just trying to go for the current player is how many chains we have, and really trying to optimize that larger numbers will come when we have larger chains from right here. And so count the number of chains the other player that match the found length. So if we have the longest length, how many do we have? And we want to optimize that we have the most possible winning paths versus they have the least possible number of winning chains. So back to the original board we had again. We go from our moves. We go from the next, still not terminal, down to the terminal node. We're done from here. This will give an evaluation of 3 because we have a length. So, like, okay, the longest one for us is 1. Like, so 1, 2, 1, 2, 1, 2, 1, 2. But we have 1, 2, 3 of these from right here. Because this is not a length. These are tied off from right here. So where we could. So get 3 coming up. Evaluation, next move they could make, coming down to here. Here it's a win, so it's automatically put that as the highest to 99. Come up here, the evaluation from here we're trying to minimize now. So this is going to pick the 3 coming out of here, and we have that one evaluated. Go to the next choices. Okay, terminal node, they win, so now it's getting minus 99. We can still keep doing moves. Go to our turn. We have a win from right here, so it's 99. Comes up here, minimizing, because even though this is a win route for us, it'd be an automatic loss route coming down from this node here. So 99 goes up because we're minimizing on the level where it's their turn. Then the next, their win, so again 99. We have 3. Minimize between the 2 is 99 is going up. And just saying is that if we pick this or this, they're going to automatically win each turn. So we have them evaluated better. So the choice this time will be here, will be the 3 picking this one. Because we have a better chance. We have a chance for winning. We don't know if they're going to win further down here based upon other moves they can do, but we can already know. If we come down to this state, if they make this move, we're just going to go to a draw. If we go to this move, we're going to go to an actual win versus where we would have had the losses over here. This is a later playing in the game. Now, that's weird. You don't have to understand it perfectly, but that's the idea of the tree and the evaluations trying to do it. And I'm not going to go through this algorithm, but this just shows a variation now called alpha-beta pruning. And the idea is that this tries to stop the evaluation as you're going down. If the results keep getting worse, it basically prunes off a branch before going down to a terminal state when it realizes the scores as it's going down are bad. And so it's supposed to help you that if you can run this algorithm to go further and deeper into that actual algorithm itself. Okay. Now before ending things, because I just want you guys to play around with this and understand it and have the basic idea of an actual game tree, there is now actually posted with the notes, it's called the connect end. So posted with the notes is a whole system. So if I switch back to my other screen, right here, there is a connect end game. You can see it here. Right here. So this is a larger one. So what this is, I'll just open up the basic one. If you've ever played Connect 4, or if you want to go look up the game Connect 4 now, that would be a good starting point. But there's an explanation of this. So this one here, it just means that you're playing Connect 4 where you drop tokens as you're going down. So you have the choices. You have tokens that are going to be dropped from the top and then fall to the bottom. And what you're trying to do is make a connection of, usually if it's Connect 4, you're making a path of 4 tokens of your side together. Connect N is a variation that I've set up for this where you create board sizes of N by M, so larger, and then you can have larger chains. So basically making this a more complex game, and you're trying to win by getting a chain of N tokens on the diagonal or straight or up and down that you can actually, boom, win with. And so here what this system does is it allows you for you to completely play it against someone else, but also then to create your own AI. So if you want to look under here of the Jordan Kidney player, you'll see examples of the alpha, beta, and min-max algorithms, and you'll see 3 different evaluation functions. There's lots of extra code here, but what you'll see is here's like 3 calls doing min-max and using each one of the evaluation functions, and from right here, and then our final AI choice maker. So the AI choice maker is the actual player, so doing the AI for this system, and then right here is where it actually sets what algorithm is going to use. So right now, default for the system, it's using the min-max algorithm using the evaluation 1, but you can change this to be the AI min-max, like 2 or 3. You can change which ones you want to use this for. So there's all the different ones that are within here. The game lets you actually play it. You've got the game board itself. If you're curious about making your own AI player, you can take a look at the code to see if you understand it, or you can talk to me about it. But right now, if you just want to play it, you can look under the individual game player here. And all these different classes are just different starting mains that allow for different players to go in. So one here where it's making here the 2 AI players is player 1, player 2, makes the actual game, passing them in, and this starts saying the actual, if you're looking for right here, is the number of rows and the number of columns in the actual board that you can have, so row columns. Then the actual win length, this is just delay, so when it's playing it there's a little delay before going to other choices, and then saying who's winning. And so when it says AVA, that means AI versus AI. A versus L is just playing a left to right linear picker, so it just goes from left to right dropping tokens, everything else. So, and then we have U, it's user player. So let's just say if we do U and I want to play against the linear picker, which is basically a for loop for right now. You can see the beginning board for right here is showing the columns. We can then pick a choice in between these. So I'm going to pick column 1 as my choice. So you'll see player 1 and then there player 2. Now player 2 is just going to always keep moving this way. So you see if I do column 2, they just go above me. If I do column 7, they just go to column 3. Same thing if I do column 6. They're just continuously moving forwards with this, and we're just trying to get to where we can have a win state. And they're easy to beat because they're just going to keep doing that linear step. So even if I just start going like 1, 1, 1, 1, there's a good chance that I could end up winning. 2, 2, 2. Or we'll go 5, 5, 5, 5, 5. And so forth. So from right here, saying that even I won from there, and they're easy to actually trick. Now a different one we could play is playing against the user plays the AI with that one evaluation function. Right here. So user versus AI. So we'll be player 1, they're player 2. I will start, and I'll just try to beat them with some strategy. I'm not down this because we're doing the video and I want to sit here playing this forever. But you can sit down there and playing it. So they're doing the evaluations. They're going through the game evaluation, looking to the future to certain depths and playing with it. I will then do 4. Right here, I will try to block them off. Boom. So there you go. I at least got them to being a tie, but neither of us was able to actually win. But even faster, we can go and even just quickly watch an AI play the actual AI itself. So win length of 5, different boards, go through the delay. And we watch where we have the AI playing another AI. So boom, neither of them won. Still even got them both to a draw. Same thing again. The idea is that you can come in here, you can change these. There is ways to do tournaments where it runs every combination you can have. You can play with this and make things, say, larger. Let's say we do like 20 by like 15 board and have a win length of 10 right here. And just let them go at it. You can also see it slowing down. Doesn't seem to be moving faster because the idea this is a lot more possible choices. There are a lot more possible branches since there's 15 possible choices until a column's full here. So it means every parent will have 15 children until a column is actually full. And this is where it's nice that things, and you have the two AIs are both doing this, so even as you keep doing it, this could take a like freaking long time. I will terminate this now. And we can even start speeding it up quickly. And I should end this soon. It's fun to play it around. It'll only have a delay of like 10 milliseconds. As they battle it out between player 1 and 2, which even though this is text-based, it's kind of hard to see who's winning at what time. Colors would be nice, but I don't want to rewrite this program to do it with graphical designs right now. If you want to, please go ahead. But you can see this is going to take way too long. Even I don't want to sit here. I'm only going to run this once more. You can already stop now. We're basically at the end. Ooh. Whole computer slowing down. Let's even go back to like 10 by 15. Only having to have a win length of 7 and set the delay. And now let this go. So there's less, say rows. Yeah, I'll go with the less columns. 10 by 11. Win length of 6. A little bit faster, less choices they have to make, only 11 this time. Wins could be a little bit better. Oop, getting to almost a draw again. Oh, board's full. Neither one. Played each other out. Okay, I'm going to stop there. That's enough doing this. You guys can go play with this. It's a full system. You want to see the actual algorithm in play, doing the recursive choices, and playing a game. Other than that, I hope that all of you are doing fantastic and continue being the great people I know you are, no matter how you're doing in a course, no matter what grades you have, you're still awesome people, and I just want you to keep moving forwards and keep learning.